And thanks for the opportunity to present our work. Thanks for the opportunity to present our work in this meeting. So I will speak on local quenches and quantum chaos from higher spin perturbations. This talk is based on work with Justin David and Prem Kumar. So we begin with considering a CFT with an entanglement interval from L1 to L2. In this CFT, an excited state is inserted at origin at 0 time, shown by this red blip. And this excited state has a width epsilon. Under time evolution, this excited state evolves and propagates along the light cone. And at the time equals L1, it encounters the entanglement interval. So what this means is that the entanglement entropy of this system changes when the excited state encounters the entanglement interval, and there is a jump in the entanglement entropy. What we study in this system is that we look at local quench. We show that when time is here, like it is at L1 plus L2 by 2, and epsilon, the width of this excited state, is small, then the quench correlator can be analytically continued to the out-of-time order correlator. This will enable us to extract the Lyapunov exponent from the quench correlator. Another thing that we consider in this work is that we consider local quench in one CFT of the thermophile double. So what that means is this is one of the CFTs in the thermophile double, and the other CFT is just, it does not have an excited state, it just has an entanglement interval. So the holographic dual to this setup is a Kruskal extension of the BTZ black hole, shown here, with an infalling massive particle which starts its motion at a distance epsilon from the boundary at some time, and it falls towards the black hole horizon. And this infalling particle is only in one region of the Kruskal extension of the BTZ. What we're interested in is to, so this is the diagram of just one time slice. So what we're interested in is to consider entanglement intervals on the two CFTs. The vertical lines are the CFTs here, and evaluate the mutual information between these two entanglement intervals. So the mutual information kind of, it measures the correlation between the two regions, between the two systems, and due to the presence of this excitation here, the correlation dies off. So the mutual information becomes 0 at some point, and the time at which the mutual information becomes 0 is called the scrambling time. And this is what the scrambling time looks like in this setup. What we tried to do in this work is to evaluate the corrections to scrambling time and Lyapunov exponent when this infalling massive particle has a spin 3 charge. Going back to the CFT, to a single CFT.
Yes. 0 you mean becomes 1 by n. Becomes 0 you mean becomes 1 by n.
1 by, yeah, we are working in large C, yes. So let's come back to the only one CFT with an excited state. So the excited state is actually produced by insertion of a pair of operators near origin, separated in imaginary time by the width epsilon. And the reduced density matrix of this system is given here. It is obtained by taking the thermal density matrix and acting on it by the excited state operators O and O dagger, and then evolving in time. Epsilon here is a regularization parameter, which is also the width of the excited state. So this gives the reduced density matrix to be of this form. The O dagger operator locations are shown in this holomorphic plot to be these x1 and x4, and x2 and x3 are the twist locations. So we want to evaluate the entanglement entropy, and the twists are located here. The entanglement entropy is obtained by taking trace over A complement. This region is A, so taking the trace over the region except the entanglement interval, that gives just a 4-point function of the O dagger operators and the twist fields. So the holographic dual to this CFT setup is a BTZ black hole, which is shown here. The CFT is on this vertical line, and a massive particle is inserted in this background, in this BTZ background, which starts from a distance epsilon from the boundary and falls towards the black hole horizon. This presence of this massive particle, it gives rise to a back-reacted geometry in the bulk. And the back-reacted geometry is then given by the conical defect geometry given by this metric. M is the mass of the infalling particle, which is related to the conformal dimension of the excited state operator in the field theory side, given by delta. And this geometry was studied by, in this paper in quite detail. So what is done is this conical defect geometry has these coordinates r, tau, phi, and these are related to the coordinates of the BTZ geometry that are t and l by this transformation. So this transformation is how the time dependence in the background comes in. These are also the coordinates which are like the CFT coordinates, t. This L will match to the CFT L. Capital M is, it's the mass of the BTZ black hole. It's the mass of the BTZ black hole.
Are we not inserting a heavy operator?
Yes.
Which creates...
No, there is an existing BTZ black hole in which a heavy operator is inserted, and that becomes, the geometry becomes a conical defect geometry. So this geometry, this conical defect geometry has these connections, A bar. Alpha is related to the dimension of the excited state operator in the field theory. And so defining these matrices, which is exponential of A times B and exponential of A bar times B inverse, where B is rho L naught, and using the holomorphic prescription to obtain the Wilson line, this is the holomorphic prescription. We obtain the entanglement entropy, which is log of the Wilson line, and this is the expression for entanglement entropy in the conical defect geometry. The matrices L1, L minus 1, L0 are the SL2 are matrices. Okay, that C by 6 is outside the log. Yes, there is an error here. So now what we do is we substitute the transformation that was given here. Yeah, so R infinity is related to the rho here. Yes, R infinity is related to rho, so it is a coordinate, it's the radial coordinate in the conical defect geometry. Yes, so we are interested in finding a Wilson line between 2 points P and Q. So this is the location, the radial position of one point, and this is the radial position of the other point.
Rho is high.
Yes.
Rho of the
yes. Yes.
It's a regulator.
Yes, it will give a UV regulator. Yes. But I mean, this will be substituted from here, this transformation, and there is a UV cutoff over here. This lambda here is the cutoff.
And the delta tau infinity and delta phi infinity are
The two endpoints between which the Wilson line is evaluated.
in the CFT.
So delta tau is it's a conical defect coordinate, tau 1 and tau 2. And then those tau 1 and tau 2 substituted using this transformation in terms of the BTZ coordinates or the boundary coordinates. So there are the two endpoints of the Wilson line, they are both located at the boundary. That's what this means. At the boundary, I mean, it can be one boundary, or we can take one of the points to the other boundary as well.
It's a single CFT.
Yes, it's a.
It has some given UV cutoff.
Yes.
So that
R infinity is as such not the cutoff. It just means that R, the transformation is to be substituted limit R going to infinity. Yes, it's just one cutoff. This lambda.
Okay.
This lambda is the only cutoff.
Yes, yes.
So this is the entanglement entropy in the conical defect geometry. And then the transformation is substituted in this entanglement entropy, and we obtain the following time-dependent jump in entanglement entropy. This is the difference. So I showed that plot of the jump initially. So this is the difference between the two values, and this has time dependence, which is given here. So an interesting thing to notice here is that in the CFT, I said that 4-point function. So the locations, the cross ratio of the 4 points is this function given. So the cross ratio has the behavior that it has a branch cut. So essentially, when time is increased, so in this plot, this is a plot of the cross ratio. So time is increased from this point to L1 here in the upper curve, and then here it encounters a branch cut, and a cross ratio goes in the second sheet where time goes from L1 to L1 plus L2 by 2, and then when time is increased further, it comes back. So from L1 plus L2 by 2, it comes back to this branch point, and at that point the value of time is L2, and then it exits the second sheet and goes back to the first sheet. So that gives the jump here. That behavior of the cross ratio gives the jump here. Well, one of the things that we want to do with the entanglement entropy is to take the large time limit when t is around this region, that is t is around L1 plus L2 by 2, and epsilon is small, because that gives the z going to z very smaller than 1 limit. And so we want to take t going to infinity without encountering this branch cut. So to do that, there is analytic continuation of time is done. So time is taken to t plus I epsilon 1, where epsilon 1 is parametrically larger than epsilon. So what that enables us to do is to stay in the second sheet and take the time going to infinity limit. Because it is in this limit that the cross ratio is small and the time is going to infinity via this analytic continuation, that one can take this entanglement entropy to an out-of-time order correlator. So this entanglement entropy correlator, it goes to the out-of-time order correlator, which is given here. And if this epsilon 1 is put to be beta by 2, it gives the standard out-of-time order correlator, which is in papers by Perlmutter and other people. Next, we consider the Kruskal extension of the BTZ. So we want to get, one more thing here is that we can read off the Lyapunov exponent from this exponential itself, that is 2 pi by beta. But to see a more cleaner calculation of getting the Lyapunov exponent, we will information. To study the mutual information, we go to the...
so what did you calculate the finding that quantity was W?
Yes, W is the bracket here. So delta SE is log of W, and that is W. The bracket there is W. That is, I mean, in the field theory, it gives that 4-point correlator of heavy, light fields.
So your delta S entanglement entropy is
log of this quantity. Yes.
And then you expand.
No, this itself, like this, this correlate. I mean, this Wilson line fundamental. This itself gives the OTO. This is.
So, but to get the delta S, what do? You take a log of this?
Yes.
Take a log of the whole.
Yes.
You remove the sign of the quantity.
Yeah, because this is delta SE, so yeah.
And then the time dependent part is log of 1 minus that constant times e to the power 2 pi
Yes.
log of this star.
Yes, it remains exponent.
One goes away.
Yeah.
The one goes away.
In the limit of large time.
Oh, okay. This 1 over c, of course, you write that as the scrambling time. So t minus log c. I see, got it.
I mean, there'll be a cleaner calculation with the mutual information for the scrambling time.
Yeah, got it.
This is the holographic dual to. So this is when the Kruskal extension of the BTZ is considered with an infalling massive particle. This is holographically dual to CFT in a thermophile double, where in one of the CFTs there is a local quench, and we evaluate mutual information. So these two are the CFTs, left and right, and there are two entanglement intervals on the CFTs, A and B, and we want to evaluate the mutual information between them, which is given by this formula. A union B is the union of the two intervals entanglement entropy. So because of this infalling particle, this gives rise to a conical defect geometry, a back-reacted geometry in the bulk. And again, there is a transformation which relates the coordinates of the boundary to the conical defect coordinates. However, the transformations in these two regions are different in the left and the right region, because in one region there is the particle and in the other region it is not there. So the transformations are different. And these are the two different transformations, left and the right. Notice that the transformations are related to each other by the replacement of the time going to t, time in the right region going to time in the left region plus I beta by 2. Again, we use that same formula for entanglement entropy derived earlier in the conical defect geometry given here, and we substitute tau and phi. So what we want now is A union B entanglement entropy, and if we look at one of these lines, the blue dashed line, it goes from R1 to L1, points in the right boundary to a point in the left boundary. So what is done in this formula is that tau at L minus tau at R, and the two different transformations are substituted here. So that is how we get the mutual information, and then we study the mutual information in the limit of large time and set it to 0. And from there, one gets the scrambling time. Here, this substitution is done where delta, the conformal dimension of the CFT operator, is substituted in terms of epsilon and energy. Energy is finite. So essentially, we take the delta to be small by doing the substitution, and in that limit, the scrambling time is given here. So the S density is the entropy density, thermal entropy density, pi c by 3 beta. So Lyapunov exponent is read off from this scrambling time by considering the coefficient of the log c term. And in this expression, the coefficient of the log c term is beta by 2 pi, and that gives the Lyapunov exponent to be 2 pi by beta. In the charged conical defect geometry, this is the metric, and these are the connections. W is the spin 3 charge, which is related to Q in a certain manner. This is the expression for the Wilson line. Wilson line is the line connecting, any 2 points. This is the expression for it in terms of the cross ratio Z. Cross ratio is, it's the cross ratio of the CFT points, the 4 points on the field theory side. And using the substitution of delta being small of the order epsilon, and the spin 3 charge being of the order epsilon square, and a constant Q, this is substituted, and we get this single-sided entanglement entropy. We look at this particular limit of the single-sided entanglement entropy, that is the length of the entanglement interval going to infinity, and followed by time much larger than L1. So in this particular limit, this is what is obtained. So if you notice that this quantity is real, this log is real and finite only when Q satisfies such a bound. So what that means is that the spin 3 charge W has to be less than square order of the dimension of the of the excited state operator. So this is the bound that we find. In a recent paper, people have Perlmutter and Hartmann, they have found a stronger bound than this, but their arguments are also much more general. So another interesting regime to look at is, as I had mentioned earlier, this out of time order regime. So for this, time is between L1 and L2, and then time is analytically continued to t plus I epsilon 1, and then the t going to large limit is taken. So this gives us the out of time order correlator. Scrambling time is evaluated from the two-sided Wilson lines, which is given here, and then the scrambling time that we obtain with the correction of the spin 3 charge is given by this formula. So so this is the scrambling time, and we notice that the scrambling time increases as Q is increased from 0 to a critical value, the same critical value that the bound that we found in the previous slide, and it is singular at this critical value, and then it decreases. Also notice that when energy is small, this E, if suppose it can be neglected, then if we look at this expression, it goes as log C, but with a different factor in front, beta by 4 pi. In this paper by Perlmutter, he defines spin 3 scrambling time as T3 star beta by 4 pi log C. And so we kind of get a holographic verification of Perlmutter's result by this calculation. Another thing that...
The case that it is proportional to n minus 1, that is a concrete calculation or a conjecture?
It's a CFT calculation, it's a concrete calculation, yes. We also look at conical defect that infalling particle has a high spin chemical potential. In that case, all the results of the charged case can be generalized to the chemical potential case by just substituting the chemical potential in terms of the charge by this formula. So till now what I was talking about was the background in the bulk was just BTZ in SL3, and then it had an infalling massive particle which had a spin 3 charge or chemical potential. But now what we will talk about is that the background itself is not BTZ, it is a BTZ with higher spin chemical potential, a higher spin current, and there it has an infalling massive particle, but now this infalling particle does not have any high spin charge or current. So the holographic dual, the CFT dual to this is can be obtained by such an action where the CFT action is deformed with a higher spin current W, and in this CFT and its thermophile double, one can calculate the entanglement entropy between the left and the right regions, and the entanglement velocity. So in this entanglement entropy in the limit of large interval length is given by this formula. So it is 4 times T times the thermal entropy density, and V is defined using this equation, and for an unperturbed CFT, entanglement speed is 1. What we find is that V remains unaffected in the presence of the higher spin deformation given here, and in the presence of the deformation, the entanglement entropy still remains 4 S beta times T, and V remains 1. So this is all in the limit of large interval length, L going to L much larger than beta. Another interesting thing that we see in this particular CFT calculation is that the entanglement velocity, so the blue curves in these plots, so this is a plot of the derivative of this left-right entanglement entropy, the time derivative of this left-right entanglement entropy divided by 4s beta. And this is the plot when the complete mu correction is kept. So we do not do any expansion in orders in mu. The blue curve is when there is no perturbation by the chemical potential mu, and the red curve is when the perturbation is there. So what we notice is that the red curve, it approaches the blue curve from below, and so it kind of approaches the velocity, the entanglement speed equals 1 in this region as time is taken to be large. And in these two plots, it approaches it from below, the speed V equals 1. Whereas in this particular plot, it approaches it from above. So we kind of find a bound on mu for the mutual information to remain a concave function, and that is shown here. So this is mutual information is given is on the y-axis, and the x-axis is time. And if you see, if we go beyond 0.033, it does not remain a concave function. So that is a bound that we find, that is mu equals 0.033, below which the mutual information is a concave function, and the velocity, entanglement speed approaches 1. And finally, we also evaluate the scrambling time in this setup by a CFT calculation of evaluation of a 6-point function on the thermofield double. X2 and X3 are twist operators in one CFT, and X2 hat and X3 hat are the twist operator locations on the other CFT. The scrambling time is given here, and if you notice that there is no correction at mu by a log C term. So what this means is that the Lyapunov exponent remains the same as Einstein gravity. I apologize for the misspelling here. Yeah. Finally, the summary. So we consider 2D CFT at large C with local quench by operators carrying higher spin charge. We use the Wilson line prescription to compute single interval entanglement entropy following the quench. We find an analytic continuation which takes the quench correlator to the out-of-time order correlator. The entanglement entropy is finite and real only if the spin 3 charge satisfies this bound. And we find corrections to scrambling time for the two-sided mutual information in the thermofield double when the quench operator has a spin 3 charge. And we find that the spin 3 Lyapunov exponent is 4 pi by beta. We also find that the scrambling time in CFT with high spin charge, where the quench has 0 high spin charge, the Lyapunov exponent is the same as that of Einstein gravity. Thank you. Yes.
So this result 4 pi over beta.
Yes.
So how does it square with Anderson's bound? I thought that was quite a general bound derived on the basis of some general field theory argument.
It violates. It violates the bound.
Yeah. So how does it? That's what I mean. No. Malderson had a field theory argument. Yeah, Malderson had a, so gravity gives 2 pi over beta, but Malderson had an independent field theory.
Okay, so the theory violates, if you have finite spin charge, and this finite number of spin charge.
I mean, Lyapunov exponent calculation is next, but if we just look at this out-of-time order correlator, then when Q is less than this particular limiting value, then this term, it actually dominates of the scrambling time.
Yeah, by 2 pi by beta.
No, the exact answer also, the quantification. You can show the scrambling time.
Yes.